Welcome back to the lecture series on heat transfer operation. This is Yogesh Landge. In today's video, we will see the one derivation on the effectiveness NTU method. The effectiveness for a parallel flow heat exchanger. So, what happened to the parallel flow when the both fluid are flow in the same direction? So, from the graph, we will see first what exactly it is. So the red line, it shows the hot liquid, and the green line, it shows the cold liquid. We draw this graph between the x, or the length of the exchanger, versus the temperature. What is the temperature at a particular length? So as we consider, this is at 0 point and this is at L point. This is the temperature difference initially at 0 distance and the temperature at L distance. THI is represent the inlet temperature of the hot liquid. TH2 is represent the inlet outlet temperature of the hot liquid. TC1 is represent the inlet temperature of the cold liquid, and TC2 is represent the outlet temperature of the cold liquid, and delta T1 and delta 2 is the temperature difference between these two. So we draw the graph between the x, that is the length, versus the temperature. So if you see here, then the continuously when you move from the 0 to L, the temperature of the hot liquid goes down. It is down. While as you move from 0 to L for the cold liquid, then you find that there is a up the temperature. So temperature of the cold liquid, it is gradually up, and this is gradually down. Okay, so we take the same, we take the help of this, with the help of this graph and concept, and we are writing the equation in terms of the Q. What will be the effect of Q with respect to change in the length from 0 to L? Okay, so let's see the first case. Now we are solving the one derivation, that is for the effectiveness for parallel flow heat exchanger. The heat exchanger dq, this is the differential heat transfer rate through an differential area dA of the heat exchanger is given by. So we write the first the equation in terms of the dq and dA. dA stands for the differential area and dq stands for differential heat transfer rate. So we can write this equation as dq is equals to the u, that is the overall heat transfer coefficient, differential area into th minus tc. So hot liquid temperature minus cold liquid temperature. So we give, this is the equation number 1. After that we are writing these equations. So this one equation is for the hot liquid and another is for the cold liquid. Now you see here the differential heat transfer rate is equals to the minus, so here the minus sign, m suffix h cph into dth, differential temperature. Now dq is equals to m suffix c suffix pc into dtc. Now we are taking this minus sign as we seen in the last graph, that is the hot fluid temperature continuously goes down. It is gradually decreasing with respect to change the length from 0 to L. Similarly, you see here, that's why we are taking this is a minus sign, gradually decreasing the temperature for our adjustment of this equation. And for this one we are taking the plus sign. Okay, though we are not noted, it is plus sign. Why? Because gradually the temperature of the cold liquid is increases. Okay, so with the help of that one we are taking, and now we readjust this equation. So we can write this in terms of the differential temperature for the cold liquid and differential for the hot liquid and differential temperature for the cold liquid. So we noted this is differential t suffix h, this is h, okay, is equals to the minus dq by ch. So we are taking from this equation, we write this is, and for the differential temperature for the cold liquid we write this equation 2 from this one. So we readjust this one and we write in terms of dq by c suffix c, where c suffix h and c suffix c is the heat capacity rate, which is the product of mscph, that is ch, and mccpc, that is for c suffix c. After that we are taking the difference in the hot liquid temperature and cold liquid temperature. So we write this as d suffix dth minus dtc is equals to the, we are taking this one is minus dq by ch minus dq by c suffix c. And then what we do, we are writing this equation as d suffix sch is equals to minus dq in bracket 1 upon ch plus 1 upon cc, which we represent the equation number 3. So we just taking the common dq and we are writing this equation in terms of this one. Okay. After that, what we do, we substitute the value of dq. We substitute the value of dq from equation 1 in equation 3. So what we do, so this is the general equation in for the heat transfer rate. Okay, now what we do, we have this equation number 3. Now we put the value of equation 1, that is the value of dq, in equation number c in equation number 3. So what we do, we put it this here. After putting this one and the readjustment of it, we got the equation number 4, which is differential Th minus Tc upon Th minus Tc is equal to the minus u overall heat transfer coefficient into the differential area in bracket 1 upon Ch plus 1 upon Cc. So we give, this is the equation number 4. So what we do, first we write the general equation, we give equation number 1, then we are writing the equation on the basis of the energy balance equation. Okay, so these are the energy balance equation, dq in terms of for the hot liquid, for the cold liquid. Then we take the difference of the hot liquid temperature and cold liquid temperature, and then we write this equation number 3, and after that one we put this value dq in equation number 3, and we got the equation number 4, this one. Now the next step is integrating the equation number 4. So what we do, we are integrate this equation number 4 within a limit. Now what are the limit? What are the variables? The one variable is the temperature and another is the area. Area means changing the length, change the temperature. Okay, so as we see in the first graph, where with respect to the length, the value of temperature change. So here there are the two variables we kept. The one variable is the temperature and another variable is the area. So what we do here, integrating the equation number 4 within the limit Thi minus Tci and Tho minus Tco of parallel flow heat exchanger. Why we are taking these limits? Let's see. So let's consider this is the hot liquid fluid flowing and this is the cold liquid fluid is flowing. Okay, the one hot liquid, cold liquid. If you see the temperature of the hot liquid is Thi, outlet is Tho, inlet temperature of the cold liquid is Tci, and outlet temperature of the cold liquid is Tco. Okay, and we see that within this one there is a change in the value of Q. So this is delta T1 and this is the delta T2. So what we do, we are taking this limit. The first limit at the 0 point means at 0 length means at 0 area. So it is what Tci, Thi, inlet, and this is the outlet, and we are taking the another limit, it is Tco and Tho. Okay, that's why we are writing this Thi, inlet temperature of the hot liquid minus inlet temperature of the cold liquid. This is at 0 point. Okay, and this is at L point, at length L, and this is at length 0. So we consider at area 0, and here we consider at area A. Okay, so the limit is the one limit is the temperature difference, this one and this one. So lower is this one at 0 area. So what we take Thi minus Tci at area 0 means at length 0, and then at area A means at length L, it is Tho minus Tco. So we are taking limit Tho minus Tco. Okay, so we consider, let's consider this is the length. Okay, length is nothing but it is indirectly the area of the heat transfer. Fine. So we integrating the equation number 4 within a limit which is Thi minus Tci and Tho minus Tco for the parallel flow. Okay, so the condition is for the parallel. So for the parallel we are writing this type of the equation, the notations, so that we can easily understood to put up the limits of this one here. After integration we got this equation, it is Tho minus Tco upon Thi minus Tci is equals to the exponential of minus UaCH 1 plus Ch minus Cc. Now what is this Ch and Cc? Already I said it is the heat transfer rate, which is the product of mass flow rate into the specific heat. So C suffix H stands for the cold hot liquid and C suffix C stands for the cold liquid. Okay, so once we integrate within a limit and we know how to take the limit. So limit at 0 area, this one, and limit at area A is this one. Okay, So after this, we try to eliminate the temperatures, because in the effectiveness NTU method, we do not want the temperatures, because this is lacking and we have a limited the temperatures value. Okay, so what we do? So we are first defining what is meant by effectiveness. So effectiveness is what? It is the Q max, Q actual by Q max. Already in the last video we see that is the Q actual upon the Q max. So what is the Q actual? So we write this epsilon value as C suffix C. If the C suffix C is minimum, then we can write this TCO minus TCI in outlet temperature of the cold liquid minus inlet temperature of the cold liquid upon the maximum value. So Q max is what? The C minimum into the delta T max. So delta T is max what? It is THI minus TCI. Where you got the maximum delta TA at 0. So here THI minus TCI. So I writing this one. Or we can write as, if the value of CH is minimum, then I can write C suffix H is equals to the, so we are writing this as the effectiveness. So this is the one formula for getting the effectiveness, depend on for the cold fluid, and we can write this equation on the basis of the hot fluid. Okay, so here also it is CH is equal to THI, inlet temperature of the hot liquid, minus outlet temperature of the hot liquid, upon the C minimum. So this is what a Q max. Q max is what? The C minimum upon THI minus TCI, the maximum temperature difference in the exchanger. Okay, so as per the effectiveness, we are writing the equation. We give this equation number 7. What is the next case? So from the equation 7, find the value of THO and TCO. So what we do, first we try to find the value of THO and TCO from the equation number 7. So it means from this equation we try to get the value of TCO and THO. Okay, so we equate this equation number 7. After the equating, what we got? So we are equating this equation number 7, and after equating we got the value of THO is equal to THI minus epsilon C minimum in bracket THI minus TCI upon C suffix H, and the value of TCO, this one outlet temperature of the cold liquid, is TCI plus epsilon C minimum THI minus TCI upon C suffix C. So both equation we got from equation number 7 after equating it. How? See here. So first we take this one, we try to get the value of TCO. Here is the TCO. Okay, then we from this equation epsilon equals to this one, then we will get the value of the THO. Okay, from this one, okay, you just consider this one. From this case you get the value of TCO, and again consider this one is equals to the epsilon, then you get the value of THO. Okay, so once we got that values of TCO and THO, then we are putting these values in equation number 6. So we are putting these values in equation number 6. So where is the equation number 6? You see here, this is the equation number 6. So we put the value of THO and TCO. Ultimately our aim is to reduce the terms temperature, and for that one we are doing this adjustment on the basis of the definitions and the assumptions. So we find the value of THO and TCO. After that one, we are putting the value of this one in equation number 6, and then we will get the equation as the epsilon is equals to the 1 minus exponential of minus UA by CH in bracket 1 plus CH by CC upon C minimum in bracket 1 upon CH plus 1 upon CC. So this is the equation. Now here you see there is no temperature. So we call this is the effectiveness. So for the parallel flow, what is the effectiveness formula? Then this is the effectiveness formula. Okay, so here so we again try to reduce the equation. So what we consider the CH is less than CC. It means the heat capacity rate of the hot fluid is less than the heat capacity rate of the cold fluid, and for that one CH is the minimum and C suffix C is the maximum. Okay, so this is the condition. So we are replacing the CH as a C minimum and C suffix C is replaced by C maximum. Okay, so once we replace that one terms from in equation in the previous equation, if you see here, So here what we do, we try to ch is the minimum, so we put it here c minimum, and c suffix is the maximum, so we put it c max. Okay, and we write this equation as, after that one, it is epsilon equals to the 1 upon exponential of in bracket minus ua by c minimum plus 1 upon c minimum by c maximum upon 1 plus c minimum by c maximum. Okay, now what is c minimum by c maximum? It is a capacity ratio. So we write this as c minimum c maximum as c. Okay, so here again we make a changes, so we write the epsilon is equals to the 1 minus exponential of u a by c minimum is what it is. It is the NTU. We know the definition of NTU, so it is UA by C minimum. So we replace 1 minus exponential of this term, we replace by NTU plus 1 plus C minimum by C maximum is nothing but the C, and here also we put it and we get this equation. So effectiveness for the parallel flow heat exchanger, then it is the 1 minus exponential of minus NTU 1 plus C upon 1 plus C. Okay, thank you very much for watching this video.